Hi everyone, today I would like to talk about QR factorization and especially QR factorization using Gram-Schmidt method. So there are many ways you can do the QR factorization of a matrix. One way is Gram-Schmidt, which is the easiest way perhaps by hand, but it's barely used in practice since it has a stability issue. It's not robust and also it's not really fast, right? So the computers or numerical softwares are not really using Gram-Schmidt. They use other techniques. Maybe one of them is the householder algorithm, which I'm going to talk about in the next video. Okay, so let's start. So before talking about the QR factorization, let's talk about the orthogonal matrices or matrices with orthonormal columns. Okay, so assume I have vector a1, a2, ak or orthonormal sets of vectors, meaning that if you consider ai transpose aj, you get 0 if I and j are not the same, and you get 1 if I and j are the same, right? So what it means is that a1 transpose a1 is 1. A1 transpose a1 means norm of a1 is 4, right? So each vector has a unit norm and is orthogonal to other vectors, right? That's the definition of orthonormal sets, okay? Now, these vectors can be written in a matrix notation, right? So what I mean by that, you can consider a matrix A whose columns are this orthonormal sets of vectors, A1, A2, Ik, okay? Then these matrices similar to A that have the orthonormal columns, they have an interesting property that if you calculate the Gram matrix, the A transpose A, remember the A transpose A we introduced in a videos about the pseudo inverses? This is called a Gram matrix, right? So the interesting property of this matrices with orthonormal columns is that A transpose A is equal to identity. Now, A in general is an n by k matrix. Why is that n by k? Because we have k vectors, a1, a2 to ak, so we have k columns, and each vector is n dimensional. So for example, vector a1 is this, is a1, 1, a1, 2, all the way to a1, n, okay? So then A transpose becomes k by n, and therefore we have an identity that is k by k. Now, these vectors do not have any specific name. They are called vectors or these matrices like matrix A do not have any specific name. They are called matrices that have orthonormal columns or matrices with orthonormal columns. Now, if this matrix A turns out to be a square matrix, then and satisfies A transpose A equal identity, then they have a very special name. They are called orthogonal matrices. So orthogonal matrices or a square matrix, this is very important. Orthogonal matrices, I will use another color. This orthogonal matrices, they must be a square, and then A transpose A should be identity. Or they should have orthonormal columns. Okay, if these matrices are not a square, the matrix A is not a square, no problem. This again, A transpose A is equal to identity if it has the orthonormal columns, but then they are not called orthogonal matrices. So remember, the first observation is that orthogonal matrices should be a square. Okay, now let's take a look at some of these properties of matrices with orthonormal columns. So matrix A is n by n, is not necessarily a square. And we want to, and the vector x and y are any n-dimensional vectors. So let's take a look at some of the properties. Let's see what will happen to a vector x if we perform some sort of transformation with a matrix A that has the orthonormal colors. Okay, let's see what happens to the norm of vector x. So let's call y to be ax, and we want to see what happens to the norm of y. So this is indeed norm of y is actually the Euclidean norm of y, is a Euclidean norm of AX. Okay, remember that what was the definition of a norm? We define the norm of a matrix, norm square of matrix or vector to be y transpose y, right? So norm square of a vector y is equal to y transpose y. Okay, the same thing is here. AX is a vector. A is a matrix, X is a vector. The product of a matrix and vector becomes a vector. So how would you define that? You define this as AX transpose times AX, which is X transpose A transpose AX, right? Since we are not talking about the norm square, I should have a square root. Now, we know that if the matrix A has an orthonormal columns, then A transpose A is equal to identity. Therefore, this is identity. And what we get back is X transpose X, which is equal to the norm of X. So the second observation is that under linear transformation by matrix A that has an orthonormal columns, the norm of a resulting vector, vector y, is the same as the norm of vector x. So transformation by matrix A preserves the norm. That's a very interesting property. Okay. Now let's see what happens to the dot product or inner product. So here I will call y1 to be equal to ax, right? And then y2 is equal to ay. Okay, so I'm interested in calculating y1 transpose y2, which is equal to what? Is equal to ax transpose ay. And if you do that, you will see that again ax transpose becomes x transpose a transpose ay, but again this is identity, so we get x transpose y back. So under orthonormal transformation, the inner product also remains the same. Okay, now we know that the inner product is the same, also norm also is the same. What does it tell us about the angle? Let's take a look at the angle between two vectors. Remember, we had this definition. Let me just remind you the definition of a dot product of two vectors. X dot y is equal to norm of x, norm of y times cosine of theta, which from here, cosine of theta is equal to x dot y over norm of x, norm of y. Now, from here, without taking any arc cosine, you will see that if under the orthonormal transformation, the inner product remains the same. So this part remains the same. And the norm of each vector also remains the same. Therefore, the angle between them also remains the same. That's one way to see that. Another way is just to carry out this calculation. We are trying to find the angle between AX and AY. Okay? This is going to be equal to arc cosine of. So what I'm doing is to take arc cosine from both sides of this equation. So I get theta becomes arc cos of x dot y and norm of x, norm of y. Okay, good. So what's going to happen here is that here you will have again what? X transpose A transpose AY, but this is nothing but identity. And here norm of AX, remember what was norm of AX? It's just norm of X. And what is norm of AY? It's just norm of Y. So this one, the angle between AX and AY is nothing but the angle between X and Y. So on the normal transformation, the angle between two vectors also remain the same. So remember the inner product, the norm, and the angle between vectors remain the same. Okay, so this is for the properties of matrices with orthonormal columns. Now let's talk about the QR factorization. So let me just tell you what is the QR. So the Q in the QR refers to matrices with orthonormal columns. With orthonormal columns. They don't have to be square. And R is the upper triangular matrix. Upper triangular matrix. So during the QR transformation or the factorization or the decomposition, we are trying to write the matrix A, any matrix A, as a form of Q times R, where Q is a matrix with the orthonormal columns and R is the upper triangular matrix, which has a positive elements on the main diagonal. But we will talk about that and why this is the case. So now let's talk about this formally. So let A be n by k matrix, so it's not a square, with linearly independent columns. Okay, the columns are A1, A2, all the way to AK, right? So since it has a linearly independent columns, recall from our pseudo-inverse or left inverse and right inverse video, we know that A is either tall or a square. Okay, very good. Now we define a Q to be another n by k matrix, and the columns of the Q are Q1, Q2, all the way to Qk. Maybe a picture will help us here. So this is A with the columns A1, A2, all the way to AK. Okay, and what is Q? Q is nothing but this Q1, Q2, all the way to Qk. Now, what are these Qs? Since I already talked about the Gram-Schmidt, I can tell you exactly what these Qs are. These Qs are the A's, but after I apply the Gram-Schmidt to the vector A's. Remember in the Gram-Schmidt algorithm, every time I take one of these vectors, I apply the Gram-Schmidt and I make sure that these vectors have a unit norm and they are orthogonal to any other vectors in a set. So in the first iteration, you take A1, and from A1, you convert it to Q1. Then you add A2, right? And from A2, you find another representation. You subtract A2 minus the orthogonal projection of A2 on the Q1. So that one, we call it Q2. If you keep doing this all the way to AK, you get Q1, Q2, all the way to Qk. So we know that, therefore, that these Q vectors, the columns of matrix Q, we know that they form an orthonormal set. Why? By construction, by design, right? Remember the Gram-Schmidt? It forms the orthonormal basis vectors, right? So we know that these Qs, this Qi transpose Qj, is equal to 0 if I is not equal to j, and is equal to 1 if I is equal to j. Okay? Therefore, if these Q vectors Q1, Q2, all the way to Qk are the columns of a matrix Q, therefore I should have Q transpose times Q equal to identity, right? That was our definition of matrices with orthonormal columns. Okay, so that's this. Now, let's take a look at a little bit of a proof here. Remember from the Gram-Schmidt video, I talked about the algorithm and the general algorithm, and I introduced 3 steps to perform the Gram-Schmidt. Step 1 was to find this Qi bar, which is the unnormalized version of Qi. Okay, what was that? It was equal to, how do you get Qi bar? From the vector AI, right? So a little bit recall. So the thing is that, let's say that, for example, you construct already Q1, and then you have a vector here A2, right? And this is Q1 with the unit now. If you want to get Q2 from here, what you would do, you're gonna find this vector, right? Which is orthogonal to Q1, and it's gonna be what? It's gonna be A2 minus A2 dot with Q1. Remember, with the normal Q1 is 1 by construction times Q1, right? So I call that one in that video V2 prime, but here let's call it, for example, Qi bar. Or here I call it Q2 bar, for example, right? And then this is the unnormalized version. So this is the same thing. We are in the ith iteration. This is equal to AI minus orthogonal projection of AI on Q1. So remember, on every single basis for that subspace, right? So on Q1, this is this, right? This is just a dot product. AI transpose Q1 is just a dot product. Instead of this, you can just write AI dot Q1, right? Okay. Now, orthogonal projection of AI on Q2 all the way to orthogonal projection of AI on QI minus 1. Okay, very good. So that's a QI bar. Now, I'm going to do some simple manipulation. I'm going to bring QI to the left side and everything else to the right side. So I'm going to end up with this. All I'm doing is in this step is to bring AI here and the QI bar here. Okay, so or another way to think about that is, because I want to make all the negative parts or these negatives to be positive, all I'm going to do is I let AI to remain in this side and bring all these terms to this side. Okay, very simple modification to this equation. Okay, so I end up with AI equal to this. Remember, what is AI? AI is the ith column of matrix A, right? After all, we need to understand what are these terms intuitively, right? AI is the ith column of matrix A, and Q1 is the first column of matrix Q. Qi minus 1 is the I minus 1 column of matrix Q. Okay, good. Now, remember in that second step, I said if Qi bar is 0, we terminate. The vectors are linearly dependent. But here I said that assume the columns of matrix A are linearly independent. So we don't need to go over the second step. What do I do in the third step? In the third step, what I do, I am going go ahead and define a vector Qi to be the normalized version of Qi bar over norm of Qi bar. Remember? Okay. All I'm going to do, I'm going to go ahead and replace this Qi bar, this one, by its equivalent. I'm going to go ahead and multiply these two terms by each other. I get Qi times norm of Qi bar. I get this one. Okay. Then I'm almost done, right? So I just need to define some terms here. So we know that this Q1, I have Q1, Q2, Qi minus 1, and I have Qi as well. So I exactly form the matrix Q, this matrix with the orthonormal columns. Remember, it's not a square. It doesn't have to be a square, right? So you cannot call it orthogonal matrix, right? All I have to do is just define these terms. I let this Qi transpose Aj for I less than j to be Rij. Okay, so you might say, why Qi transpose Aj? Why not Ai transpose Qj? So these two are the same. Remember, the dot product of x transpose y is equal to y transpose x. So here you can write this Q1 transpose Ai. Okay, good. So if I is less than j, I'm going to define this Rij to be Qi transpose Aj. Okay, good. And RII means element on the main diagonal of matrix R to be equal to this, the norm of Qi bar. Now look at this. RII is an element on the main diagonal. This is a key that you need to remember, right? It's positive. It's a norm. It's a positive. So RII is always positive. And then Rij is 0 for I greater than j. Okay, very good. So it's an upper triangular matrix, right? Because I greater than j means you're talking about this side of matrix. This is the main diagonal you're talking about here. Okay, so that's how they define the upper triangular and the Q matrix. So you exactly construct the Q matrix here. You have Qi, you have Q1, you have Qi minus 1. And this AI is each column of vector matrix A. Okay, so here I write it in a better format for you. I start with Q1, Q2, right, all the way to Qi. Then you see exactly matrix Q here. Therefore, you define two matrices here. Matrix R, which is the upper triangular matrix and is a square. Remember, upper triangular, lower triangular, diagonal matrices, they are all a square, right? Remember, identity was X, one of the special form of diagonal matrices, or one of the special form of upper triangular, triangular matrices, lower triangular matrices, right? So R is always a square. It's K by K. Why is it K by K? A is QR. A is N by K, right? Q is R, A is N by K. Let's see. A is N by K. Okay. Q is N by K. R is K by K. Must be K by K. Right? Okay, good. So here I define it here. R is this upper triangular matrix, which element on the main diagonal is always positive, with positive diagonals. And what is this Q? Q is the matrix with the orthonormal columns. What are the columns of Q? Can be easily found. You just apply Gram-Schmidt to the columns of A. Okay? Now you might be wondering, I know how to find Q, right? And I have matrix A. How can I find R? Easily, right? You let A to be equal to QR. That's what you start with. We know that Q has an orthonormal columns. Remember the properties that we introduced before? I'm gonna go ahead and multiply this equation, this one, by Q transpose from the left side. What I'm going to get is Q transpose A is equal to Q transpose Q R. Okay? What is this Q transpose Q? Is equal to identity, right? And therefore R is equal to Q transpose A. Can be easily found. Okay? So that's what I also wrote down. So this is how you do QR factorization using Gram-Schmidt. First, you have the columns of A, you run the Gram-Schmidt algorithm, you find the Q matrix, and then after that, you're gonna go ahead and multiply Q transpose by A, and then you find R. Very easy. Okay, so now let's talk about a very interesting property, which is that a QR factorization of a matrix is unique. What I mean by that is that, let's say we want to find the QR factorization of matrix A. And I claim that the Q and R that you find using Gram-Schmidt or any other method is unique, right? Now, how do we prove that this is unique? Assume we have two different representations. One is that A equal to Q1 R1. The other one is that A equal to Q2 R2, okay? And then Q1 transpose Q1 is identity, and Q2 transpose Q2 also is identity, right? Okay. And the element on the main diagonal for the these upper triangular matrices are also positive. So since the A can be written by Q1 R1 and Q2 R2, therefore these two are the same, right? Therefore this Q1 R1 is equal to Q2 R2. Go ahead and multiply this equation. I call it equation, let's say A by Q1 transpose from the left. But if you do that, you will see that this term become identity, right? Because of this. And then you get R1. I'm going to go ahead and call this one equation B. R1 is equal to Q1 transpose Q2 R2. Okay? And then if you go ahead and multiply both sides of this equation B by R2 inverse from the right, you obtain the equation 1 here. Okay? So this is one equation. The second one is that you see this one, this equation that we have, right? Now go ahead and multiply it by Q2 transpose from the left. And you get this equation if you simplify that. And then you obtain that Q2 transpose Q1 is equal to this, R2 R1 inverse. This is equation 2. Okay? So now, if you compare equation 1 and 2 together, what you end up with is that one of them is transpose of the other. What I mean by that, if you go ahead and write Q1 transpose Q2, transpose, you get Q2 transpose Q1, right? Which is this one. So the right hand sides also should be transpose of each other. If you go ahead and transpose the right hand side of equation 1, you should get the right hand side of equation 2. Okay. So what is going to happen is that you get this R2 inverse transpose, you get this here using properties of the transpose, and this R1 transpose comes here. They switch their place, right? You get R2, R1 inverse. Now, go ahead and do this one step by step. First, go ahead and multiply the both sides of this, I will call this equation 3, by R2 transpose from the left. Why do I do that? I want to get rid of this stuff, right? This is R2 negative transpose. I'm going to go ahead and multiply by R2 transpose. Okay, so for the right hand side, I get R2 transpose, R2, R1 inverse. Then go ahead and multiply this one by R1 negative transpose from the left to get rid of this stuff, right? So I get R1 negative transpose. And then if you do that, this term becomes identity, right? And then we end up with this equation equal to identity. Well, this equation is nothing, right? This equation is nothing but this one. It's just R2 transpose R2, right? And this term is nothing but R1 transpose R1 inverse, right? Because if you use the property of inverse, you get R1 inverse times R1 negative transpose, which is exactly the same as this. But look at this one. They are equal to identity. R2 and R1, both of them are square matrices. And R2 transpose R2 also is a square, R1 transpose R1 also is a square. This means that R2 transpose R2 is the inverse of R1 transpose R1, or the other way around, right? Therefore, R2 is equal to R1, right? And when R2 equal to R1, then Q2 is equal to Q1. There are many other ways to prove this one, but this is just a little bit of proof to show that the QR factorization of a matrix is unique. Okay. Okay, so now let's talk about the pseudo-inverse using QR factorization. So if matrix A has a linearly independent columns, then we know that it should be either tall or a square, right? Therefore has a left inverse, right? So now I'm gonna go ahead and write matrix A as a form of QR, where Q transpose Q is equal to identity. Then I know that what was the left inverse of a matrix? What was the pseudo-inverse of a matrix? It was this. Right, it was this expression that I have here. I have already written here. That was a left inverse of a matrix. Now I let Q A to be QR and A transpose to be R transpose Q transpose. And I just go ahead and calculate this expression. Right. If you do that, what do you get? You get R transpose Q transpose Q. R, these two become identity. You get R transpose R inverse times R transpose Q transpose. Right. So you get this. But you can simplify this further using properties of inverse. This becomes R inverse, R negative transpose, R transpose, Q transpose. But these two cancel out. So you will end up with R negative inverse, Q transpose. Okay, so that's how we calculate the pseudo inverse using QR. Okay, now assume that A has a linearly independent rows. Therefore, it's a right invertible. This was a right inverse of a matrix. Okay. Go ahead this time and let A transpose to be equal to QR, right? Let A transpose to be QR. Therefore, A to be R transpose Q transpose. And now calculate this expression here. So the pseudo inverse is equal to A transpose, which is now QR, times R transpose QR, which is this expression we're trying to calculate, right? If you simplify this expression, you will end up with this. This is going to be the right inverse of a matrix using QR. But wait, we could get this one easier. Look at this observation that I have, right? We could get this expression much easier than this. Think about that. One of them is a left inverse, the other one is a right inverse, right? Remember when I was talking about the properties of an inverse, I said one of the interesting properties is that A inverse transpose is equal to A transpose inverse. Consider this pseudo inverse to be similar to inverse. They are not the same, but consider them to be similar. So it turns out that one of the interesting properties is that A pseudo inverse transpose is equal to A transpose pseudo inverse. Okay, so what are we doing here? Let's take a look at left inverse of A. This is the left inverse of A, right? So R inverse Q transpose. This pseudo inverse is the left inverse, right? So it's equal to what? It's equal to R inverse Q transpose. So if I transpose that, I should get the right inverse, right? I don't need to even calculate the right inverse. If I go ahead and transpose this, I should get the right inverse. Let's take a look at this. Let's transpose this. I get Q or negative transpose, which is exactly this one. So thanks to this observation, right? If you have a left inverse using the QR, you can just transpose that to get the right inverse, right? And that's what this is a proof why this expression is correct, right? So what this one says is that this observation says is that you can first find them pseudo inverse and then transpose it, right? This is equal to first transpose a matrix and then find the pseudo inverse of a matrix transpose, right? That's what we did for the right inverse. We find the QR for A transpose, right? So these two are the same. Very good. It's a very interesting property. Therefore, I said that if let a pseudo inverse be the left inverse of A, then it's equal to the right inverse of A transpose. This is also another proof that I have here, if you would like to see that. I also talk about this in a pseudo inverse video, right? If B is a left inverse of A, left inverse, right? Then B transpose is a right inverse of A transpose, right? So that's also another proof for this expression. The bottom line is that if you have a left inverse, transpose that, you get a right inverse, right? For the using the QR. Right? Now, if the matrix A is a square and has a linearly independent columns and rows, then the QR, finding the A inverse using QR is very easy, right? It's just you write this QR to the -1 and using properties of the inverse, you get negative R inverse Q inverse. Okay, so that's become A inverse. So that's it for this video. In the next video, I'm going to talk about the QR factorization using householder algorithm. Thank you so much for the listening.